Now we're going to start lecture 3 on the layers of fire protection. Before we go into the layers, I want to pose to you a context that is important for fire engineering, which is one of the drivers that keeps fire engineers busy. And is the fact that the buildings where we live, the buildings and the homes where we live are different. Every year are different. We go back in time, you could see that the materials, the structures, the spaces, the materials that are inside, that we put inside, are different. That creates a different hazard and a different risk. And that's good in the sense that innovation in the building environment is something positive. We citizens have come to enjoy that, to have better homes with different spaces that are better and more affordable. But that is also making fire engineers have to catch up with innovation, because the arrival of new materials means that the fire engineers have to understand what is the risk and the hazard introduced by these materials and how to address it. And the arrival of new spaces and new buildings and in general innovation means the fire engineer has to also learn how to bring safety in those systems. And we typically say that is the innovation comes from the architects and from the building industry and for the desires of people. And engineers tend to have, fire engineers tend to be behind trying to catch up. When innovation moves forward too much respect to the knowledge that we have of the fire hazard, this gap could become a risk. So there is a need we promote innovation, but we also need to promote the understanding of the fire hazards that they might bring in. And when this gap between the innovation of new systems and materials and the safety knowledge that we have of them, when this gap is too large, we end up in situations that need to be addressed. In the context of innovation and safety, fire engineers can typically choose between two approaches into helping for the design of a building that is safe. Fire engineers can do this through prescriptive design or performance-based design. There are two ways of doing design. The two of them are equally valid if they are done well, but the two of them allow to do different things. So the prescriptive one is what we've been doing as fire engineers for a very long time, literally hundreds of years, and it just is a process where there is a book, a very thick book, it contains the recipes of how to do things safe. And if you follow the recipe line by line, all the instructions, and you follow what the book says, what the book is prescribing, then authorities and institutions will be assuming that you made a system that is safe because you follow the instructions, the previous knowledge that has been accumulated that resulted in these books of laws and standards and regulations. The problem with this is that prescriptive code doesn't catch up well with innovation. Prescriptive code moves very slowly. It's very cautious. Is quite solid, but it doesn't do well with innovation. It's difficult to change this book at the pace, catching up with new things and new materials arriving. The other approach is much more flexible, much more modern. We're talking about something that happened since the year 2000, and countries like New Zealand and in the UK, but other countries are still not doing it. That's the performance-based. In performance-based, you don't follow instructions, you prove to whoever is interested in knowing these, authorities, owners, and residents, you prove to them that the building is safe. So you don't assume that safety will arrive by following instructions. You actually do calculations, you do tests, you show understanding that shows the building is performing as it needs to perform. That gives that safety. These two approaches are quite different, and the combination of the two is the recipe for success. The ability to say, well, this I can do safely and well through prescriptive design, but this over here I will prefer, or my team will prefer to do it through performance-based. And the combination of the two helps to bring safety to the built environment. Now we come to the layers of fire protection. I've come to realize that this is a nice way to introduce what a fire engineer can do. The context that we already discussed is that there is innovation, there is a need to have a safe environment. This can be done through prescriptive design or performance-based. No matter how the design it is done, the elements in the engineering solution which will be many different elements. The fire strategy is a very complex mission of safety. It will come into a subset that I can identify as 6 of them. There could be more, but each of them can actually be reduced to these 6 that I'm discussing. And I'm writing down in this image that you see from the fire to the safety of the building in chronological order, more or less, as they could happen if there is a fire. The first layer is prevention. If that layer fails, the next layer is detection. The one afterwards is evacuation, then compartmentation, suppression, and the last one is structural resistance. So I'll go a little bit over each of them. But 2 things that I want to highlight is there are multiple layers, and this is called in defense in depth. There are multiple layers because no layer is going to be perfect. So it brings redundancy in the fact that if one of the layers fails, the others can catch up and mitigate the risk. So it's not just that we rely on one layer and this layer is not perfect, then the risk happens. It's the multiplicity of the layers brings a robustness of safety. And the second one is that there are, some of you might realize, well, in these 6 layers that you just described, Guillermo, none of them talks about the fire brigade. And that is absolutely true, because the fire brigade is so important that it's actually not a layer, it's a super layer, in the sense that the fire brigade can actually, it's not that it can, it acts on different layers at the same time. In particular, the fire brigades, although it has presence in all the layers, it is very important in prevention by bringing fire awareness and helping people have basic safety in their house, and it also by helping in suppression for sure, and actually even in the evacuation. So it's a super layer and is more important than any one single layer. Other super layers that are present are, for example, regulation. The national regulations of the country that, as we discussed previously in lecture 1, is the minimum level of safety below which the system will be illegal because it will be too dangerous. But in reality, there is a space above it. Regulation addresses different layers. The regulation tells us how we have to have different types of detection or compartmentation or suppression or structural safety. So it's a super layer. Another super layer, which is not in the diagram, will be insurance companies. Insurance companies which will take care of the cost of the damage if something happens. They themselves bring ways of doing things, and they are a stakeholder and a player, bringing into different safety layers. In particular, insurance companies have a tendency to put an emphasis into property protection, so therefore there will be more on making the fires being small, like compartmentation, or making sure that the whole collapse of the building doesn't happen, like a structural resistance. Now, a little bit about each of the layers. The first layer is prevention. Prevention is understanding that how a fire could develop in a given building, making people aware of these hazards through education and training, and also avoiding it from happening. So it's the 3 things. And typically, in order for a fire to happen, you need an ignition source that brings heat of some form, short circuit, overheating, a spark, a failure of a battery, and the flammable material, which typically in the 21st century are polymers or wood. And the combination of the 2 of them is when a fire happens, and that is a breach of the prevention layer. If we keep them separated, if the ignition source might be here but is not in contact with the flammable material, all the material that is flammable has a lower flammability, then we are helping in the prevention layer. The second layer is detection, which works by sensing fire. Sensing fire in the early stages. It's relatively easy to detect a fire when it's a massive plume in the horizon. The difficulty of detecting a fire is when it's early, when it's small, when the heat is not that much, when the light that it emits from the flame is not that much, when the smoke is not that much. So if we detect the fire quickly and early, then we can actually allow the other layers of protection to arrive soon. We allow evacuation to happen sooner. We allow suppression when the fire is small, etc. So detection is quite important. The third layer is evacuation, which relies on allowing people to get away from the fire as soon as possible. Away from the fire means evacuation doesn't have to be total. It doesn't have to the whole building being evacuated. Maybe the fire strategy allows for part of the building to be evacuated partially or in stages. But the important thing is, no matter if we're talking about a stage or a part of the building, is that this happens quickly. And we need routes that are safe, that are easy to follow, with signage that tell people what to do, and they get away from fire and smoke as soon as possible. The next layer is compartmentation. Compartmentation, which happens to be very important in the UK, not as important in other countries like the United States, relies on the importance of keeping the fire in their place of origin. Unfortunately, there is a fire, there has been a breach in the prevention, maybe that has been detected, maybe people are evacuating, hopefully people are evacuating away from the fire. But what we want is we don't want the fire and the smoke to start going into other compartments and start to threaten more people. So compartmentation is to make walls, ceilings, and floors, and vents and cavities such that the fire stays what it was and not growing in size. The next layer is suppression, which typically has the form of informal suppression, so to speak, with us. Maybe we have a fire extinguisher at hand, that's called manual suppression. That will be very early suppression, that's part of this layer. Maybe there is more automatic suppression, which will be a sprinkler that is installed in the ceiling of the compartment, and it automatically, when it senses the fire, or opens and tries to suppress the fire. Or it would be more the heavy-duty suppression of the fire brigades arriving with their engines, the pump engines, and having hoses and massive jets of water, all of them together, or even flooding the compartment with a gas that displaces the flammable gases and quenches the flame. All these are into the suppression layer. And then the last layer that we have is that the tower or the building should not collapse. Or at least not collapse when there is people inside. People could be residents that have not evacuated yet, or the fire brigade that are fighting the fire. When there is people inside, it's completely unacceptable to have the structure collapse. If there is no one inside the tower or the building and no one around, and it could collapse safely, that's a matter for the insurance companies and for property protection to decide if they want the tower to collapse or not. But it is not an easy step. And then engineers make sure that the tower is strong enough that it can actually not just sustain the load of gravity and wind and an earthquake, but it also can sustain the load of fire, because fire degrades the material properties of all materials, steel, concrete, brick, stone, or timber. In case of fire, it loses its ability to sustain loads. It is mechanically degraded, and it also leads to displacements and movements of the structure that further creates additional forces and loads that could make a tower on a building collapse or fall down. As we've just seen, we have 6 layers of protection. There are more layers, but at least they can all be condensed into those 6. You might remember from lecture 1 that we discussed the safest buildings that exist on the planet, or that we could think of a planet. These are not the most comfortable ones, these are not the most affordable or the most fair, but these are the safest ones. So I would like to go over each of these buildings with you again, now referring to which are the layers that are working the best in these buildings. So in the first one, for example, we have the igloo. We discussed how the igloo is a very safe building. It is very safe because of the prevention layer. The igloo would not have a particular amount of flammable material inside. Okay, so the prevention layer is relatively easy to maintain. The detection layer is not needed because the igloo itself is small. There is no need to alarm the people inside. The evacuation layer is fine because it's really easy to evacuate the igloo. The igloo is particularly good in the suppression layer because if there is a fire inside the igloo, the fire, the smoke, the flame will actually melt the ice made of in the walls, which will drip down into the fire and will suppress the fire. So the igloo is an inbuilt suppression system, not on purpose. It just is what it has happened. And then it has the structural response, the structural resistance of the igloo, which as the igloo melts, it actually starts to lose section. But the igloo is not a structurally underload system. It's relatively easy. So the best layer by far, why we say the igloo is so safe, is because of suppression, followed by prevention. The other igloo that we discussed, the other building that we discussed that is particularly safe is the bunker, the military bunkers. these bunkers of the layers they perform the best is the structural resistance. Indeed, the bunker is designed to be able to receive explosions and impact and blows, and not collapse and allow the people inside to be safe. This is the ultimate design of an engineer for a structurally robust structure that would not collapse in the case of a thermal abuse. And that's what the bunker does it. No, I don't know how many people want to live in a bunker. Definitely not me, but it would be very safe from that point of view of that layer. The third element that we discussed, the third safe structure, is the International Space Station. The International Space Station is very safe, and if we look into the statistics, it's probably actually the safest house in the planet. We cannot say on the surface of the planet, but in the planet, because it had fires. The International Space Station had fires, and the Russian stations had fires as well. But very little compared to, for example, the amount of materials that it contains and the amount of people who have been present. The layer where the spacecraft is the best is in prevention. In space agencies like NASA and the European Space Agency have put a significant amount of thought into the materials that they allow inside the International Space Station because of the flammability. Polymers in particular are flammable, but they make sure that they are polymers of very low flammability. And the ignition sources, which typically with overheating and short circuits and all these electronic devices and chemical processes, could actually become accidental ignition sources. There is a lot of thought into making sure that the flammable materials are of low flammability and the ignition sources are of low power, and that the material and the ignition source are separated. And that makes the International Space Station a very safe environment. Now, unfortunately, not many people can live there, and it's not very useful to live in space. But this is how engineers have ended up developing, or humans have ended up developing safe structures. Now, continuing on the discussion of the layers of protection, I've selected 2 case studies of actual fires that are well known to have happened, and everybody knew about them. You, dear listener, might know about this. One of them is the New York, the World Trade Center 9/11 fires, terrorist attack and fires that happened in the year 2001. And I would like to analyze how each of the layers perform in this fire. The outcome of this fire, of this terrorist attack, is very sad, particularly sad. We're talking about thousands of people who lost their lives. We're talking about the scar that it produced in the United States and pretty much in the whole world, and the consequences geopolitical that this led to. So the prevention layer. The fire was not prevented. The fire was brought by these airplanes, each of them on each of the towers, that crashed into the towers. And then the airplanes themselves and the gasoline and the fuel, the liquid fuel, the kerosene that they carry created an ignition source, a very large ignition source that then started to burn all the flammable elements of the World Trade Center, of those stories. Typically, office buildings have a lot of flammable material in the form of desks and paper and chairs and foams and all types of polymers. So the ignition source, the fire was not prevented. There was a breach of the prevention layer, and this breach was through a terrorist attack. Unfortunately, a terrorist used such a force that they managed to have a fire in the towers. The second one was detection. It was relatively easy to detect these fires in the sense that it actually came with a crash of the airplane. Even people in Manhattan were able to see immediately that these fires had initiated. And one tower to the other, they could see the fire. So the detection layer was not breached. There was an early warning system that actually was obvious and intrinsic to the terrorist attack. The second one of the layers is the evacuation. The evacuation in the World Trade Center worked. The evacuation in the World Trade Center worked from the stories of impact of airplanes downwards. Everybody, or the great majority of the people, evacuated safely from the point of impact downwards. Unfortunately, the terrorist attack actually stopped evacuation from the point of impact of airplanes upwards, and most of those people, unfortunately, could not evacuate, and this is the largest number of fatalities. So the evacuation layer was breached through the terrorist attack as well. there is very little that could have been done from the point of view of engineering to avoid the evacuation of that route being breached. The second one would be suppression. It was impossible to suppress such a big fire. Manual suppression with extinguishers is impossible. The fire brigades could not reach this high with suppression, and the sprinkler systems were knocked off completely. So the suppression layer was also breached, also by part of the terrorist attack. So we see that the terrorist attack breached many of these layers all at once, probably not on purpose. The terrorists, they didn't know what they were doing. Unfortunately, they were just that evil in this sense. But the layer that I want to discuss is the structural resistance. This is the one that is affected by fire the most. Now we know, at this time, scientifically and technically speaking, that the towers were brought down by the effect of the fires. So the fires that develop and continue burning for a few minutes, for several tens of minutes, they actually weaken the structure. They weaken the composite structure of a steel and concrete core made of concrete, and an exterior or a surrounding perimeter, a structure made of steel. This structure was weakened by the fire, and it is that structure that weakening that came with the towers down. The towers themselves were already weakened because of the impact of airplanes had actually destroyed part of the structure, but what actually knocked off truly the towers down was the fire. So the fire had a breach of the resistance layer. The resistance of the tower was not good enough to sustain these fires, and that's what brought down the towers, and which is one of the causes actually of so many deaths, and the impact of these fires is associated to its collapse. It's a very sad story. Lessons to be learned here. Well, fire safety engineering has learned a lot since the year 2001 about how to design buildings such that they can sustain fire. So the resistance of steel to fire, the resistance of concrete to fire has tremendously advanced since the World Trade Center fires create a lesson for engineers to realize that this was maybe not the layer that was understood the best. The second case study that I want to discuss with you is less well known. It happened in 1973, so it was before I was born, in the Isle of Man. This is a tiny island in the sea between Ireland and Great Britain. Isle of Man is associated to the UK, but it's actually not part of the UK. But it shares a lot of different culture and language. It also shares a lot of regulation and government style. So this happened in a big building. It was called Summerland. It was supposed to be a place that it was like a big greenhouse where people go to spend time and enjoy a warm weather that had been created indoors through having panels that were transparent and allowing the sun coming in, and it was with beautiful views of the sea, and it had all these amenities for kids to play and families to enjoy themselves in this big building. It was supposed to be summer inside the building. Unfortunately, there was a fire, and it led to a very dramatic catastrophe. About 50 people lost their life, and we're talking about hundreds of people that were inside. So what happens is, first, it was a breach of the prevention layer. Some young adults were playing outside. They think maybe they were smoking, they had matches, they had cigarettes, something happened accidentally, and they caused a fire in the outside wall of Summerland. That was the breach, right? There was flammable materials in the surrounding, immediate surroundings of this building. The fire took a while to be detected. The people who were related to the ignition source were not calling for help right away. People were not seeing the fire happening. People inside were not aware of the fire. It took a really long time for the fire to be noticed to people who could take care of this, to the emergency services. There was a very long delay to the fire brigades. There was a very long delay, therefore, to ask for evacuation. So detection was breached as well. Evacuation was breached as well, in the sense that evacuation was not well organized. It was not coordinated. People were not clear how they had to evacuate. The layout of the building was in different stories with mezzanine and open spaces. People were not clear how to evacuate. Parents realized that they were not going to evacuate without their kids, which were in a completely different area, and they had to cross the paths of evacuation. It didn't go well. Some of the evacuation routes and doors were locked because of safety concerns and security concerns, sorry. And this led to a very, very slow evacuation process, much slower than it should be. That layer of protection was breached. Compartmentation. Compartmentation was definitely breached. It was one of the major breaches of this fire because, and this might sound familiar to you, the walls of this building were flammable. The structural walls of this building, the roof that was transparent, it was made of tiles that allow solar influx to go through in, and the other walls had to be very tall and very light, were made of composite materials, and some of these composites were flammable. So the roof tiles, for example, were made of oroglass, it was called, which is a polymer that was flammable, and the walls were made of asbestos with a cavity, and the kaolin. These walls, the oroglass and the asbestos ones, are flammable. The fire that started in a kiosk in the outside managed to enter into the cavity. It started to burn inside the cavity of this wall and consume and breach the wall, spread to the fire in the roof, and then actually started to engulf the whole of the enclosure. So compartmentation was a big, big failure in this fire. Later on, it was discovered that obviously it was very controversial that flammable walls were used, and there was an inquiry that looked into this, and they realized that the regulations preventing the use of flammable walls were very weak, and that they should be reinforced, and they realized that the tests that they were used by professionals to learn about the flammability of a wall were underperforming, and they were removed and replaced by other ones. So a lot to learn from this. The structural resistance, the Summerland, the building did not collapse. It just became useless and it had to be demolished, but it didn't collapse itself. In that sense, that probably is the only layer that was not breached. So lessons learned from this fire, we learn a lot about the importance of evacuation, about the importance of compartmentation, and about the importance of not having compartmentation rely on walls that are flammable based on useless tests for flammability and based on weak regulation. That's what we learn. With this, I'm finishing lecture 3. What we have learned in lecture 3 is that there are these pillars of fire engineering that at least can be condensed into 6 elements. These are the layers of fire protection. The 6 of them are prevention. The single most important one is prevention, followed by detection, followed by evacuation, followed by compartmentation, suppression, and structural resistance. And we saw how these layers were being breached or not in 2 case studies, the World Trade Center in September 11, 2001, and 1973 Summerland in the Isle of Man. Going through this process, hopefully it has taught you now when you enter into a building to learn how each of the layers of protection might be present in the building, and therefore how safety arrives to us, safety of people, property, and the environment, and also how in these cases we can pinpoint the major failures of these fires and how they relate to different layers. Thank you very much. I hope to see you in lecture 4.